going to tell us about isotopic tracer studies of Fischer Tropsch synthesis.
Thank you very much, Steve. I have this opportunity to share some view of my view with CEO. I was a student for CEO for 4 years. He was my major advisor. He had a great impact on my whole life. Okay, not because I worked for him from scientific or academic point of view. The point of view I would like to share with you is CEO constantly tell us that life is so short, we need to enjoy our life, don't work so hard. So what we did usually is every Friday afternoon, we invite ourselves to his house. And we went there, we volleyball, have good food, sometimes food prepared by them, sometimes food prepared by us. But we barely bring any wine to the party. So usually, wine is our house. And the CEO has a very big cellar for all kinds of wine. So usually after the party, CEO will teach us how to taste the wine and talk about art and play piano for us. And one time we even go swimming deep. I know you didn't go. We started well and I went to your party. The point I'm trying to make is the reason CEOs always look so young because he's trying to enjoy his life. And so does also all his students here. And he always told me, we're not trying to make you become a Nobel Prize winner. We just want to be you a very applied researcher or successful businessman. So, I really appreciate that aspect. At the same time, because we were there, eat a lot of food and drink a lot of wine, I always thought that's free. I said, oh boy, graduate student life is really good, have good food and wine, and it's free. CEO looked at me and smiled and said, probably not. I wasn't sure what that means until about a few months ago, the CEO called me and said, hey, you need to give a presentation. I said, I'm sorry, I'm really busy, I cannot do that, I travel a lot. He said, well, do you remember there's no, you ate a lot of food and drink a lot of wine from my house. There's no free food at lunch. But anyway, so I'm really glad to be here to present some of the work I did. Today's topic is the C14 study for Fischer Tropsch reaction. Here's my name, I work for Dow Chemical Company. Here's really the major force to do the work, do all the work since Bert Davis here. The objective of this presentation is trying to share some of the interesting results we did years ago. Okay, so it's about 10 years ago. Therefore, if something goes wrong, we blame on Bert Davis. If it works out pretty good, that's CEO's honor. Okay, he has very good students. In reality, I really want to share some metallocene catalysts which Dow Chemical developed. However, because of confidential, I really couldn't do that, so I have to talk about this. At the same time, I would like to demonstrate some of the usage of carbon-14 tracer. The third aspect is I would like to share some of my personal view about when you do all those kind of research and how do you apply. Okay, I think that's something really important, especially in industry. For Fischer Tropsch, I think most of you guys probably already know that. Just in case you don't know that, it's a CO plus hydrogen to form some kind of olefin paraffin oxygenate. There's a silent reaction. If you first look at that, you say, well, that's a cocktail. But if you really think about that, for certain cases, some company wants to make olefin, and some company wants to make paraffin. So there's a lot of usages that you really can utilize. It depends on which way you handle the reaction and which way you design your reactor and so on and so forth. In here, we just try to do some kind of work to elucidate some of the mechanism here. The experimental was done with unsupported but promoted catalyst. It's a slurry reactor about medium pressure and 260 degrees C. Unless it's a special emphasized. First, let me share with you how the tracer works. Okay, I'm pretty sure Keith and some other folks probably have a lot of experience. But anyway, for example, if we do have a CO and hydrogen, you put some radioactive labeled ethanol. If ethanol serves as a chain initiator, then you will find out all the radioactivity. Here's the carbon number, here's the radioactivity, but we stay constant. Okay? If somehow the ethanol, to whatever form ethylene style stuff, then start to polymerize. So you will form polyethylene stuff, then that would be the case. Okay? If on the other hand, for whatever reason, this one become intermediate, that become equilibrium, so you will see the slope of that. Therefore, based upon those kind of common knowledge, therefore you can find out the stuff you add in there is chain initiator or chain propagator, whatever. Okay, based upon that, you will find out what is the species on the surface, hopefully. But the reality is usually you don't, you find out something else. For example, 1 propanol versus 2 propanol. The way we did it was during the course of steady state operation with CO hydrogenation. We put a trace amount of labeled propanol first, 1 propanol first. Then later on, we'll come to another state, steady state, 2 propanol. The top one is for 1 propanol. This is a gas chromatography, this is proportional counter. Proportional counter means whenever you have radioactivity, well, we can actually depict by this way. The bottom curve here is for 2 propanol. Take a brief look, you will find there's several things different. First, is the top one is 1 propanol. It incorporates a lot of radioactivity in it, right? So that means the incorporation of 1 propanol is quite a lot if you compare with 2 propanol. That's the first one. The second key point here is you need to pay a little bit attention here is the one that made by isopropanol usually have radioactivity for hydrocarbon. It's in the isomer. Okay, it's not in straight chain paraffin or olefin. It's in iso something. And if you look at this one, usually it's not. So the way that it not only it incorporates more, but also the way it incorporates different. Okay. The third aspect I would like to share with you is if you look here, have CO2. For this particular case, there's no radioactivity for CO2. But in this case, we do observe some CO2, which means this oxygenated group which connect with carbon has been chopped off. Therefore, for whatever reason, later on, it converted to CO2. That's why we observe those things. However, the thing that we really want to find out is that C3, I mean, 1 propanol is really true surface intermediate or not? The answer is no. Why? Because if the propanol add into the system is going to behave exactly like the CO hydrogenation forming intermediate, then all the radioactivity should be the same in fashion, okay? You add it together. So the reason is not because they behave differently. Okay, so this is the key point we are trying to address. It's not really what we want, but we got pretty much what we want. After doing propanol, the thing on our mind was after we chop out the oxygen, the carbon bond, what happened to the other fraction? Okay, the other fraction means that hydrocarbon fraction. What we did, we put 1 pentanol and 2 hexanol. The reason we put that because we can make that compound easily. Okay. If you look 1 pentanol, you can tell this is C5 compound. This 1 means 1 pentanol. Okay, C5, C6, C7. It's pretty much the same. It dropped a little bit because we have accumulation impact. Here, CO2, you do observe radioactivity, so which pretty much like what we expect. The chopped off CO2 formed that. However, when you look at C6, this time we put radioactivity in the 2nd carbon position. What you observe is when you chop off, we know it's going to chop off, but chop off with no radioactivity, so CO2 doesn't have any radioactivity. The interesting point I would like to share with you here is this is a 1 pentane and this is a normal pentane. You can find out when we chopped off the C5 group, basically most of the radioactivity goes to N-pentane. What that means is the fraction that we chopped off mostly goes to hydrogenate to N-pentane. So we try to deduce some kind of mechanism to illustrate that point, which you first probably have much better idea. Just stop here. Then you should notice when you chop it off, it has a tendency to hydrogenate instead of dehydrogenation form olefin. After we did some of our alcohol, we would like to do some olefin. We would like to find out the difference between alcohol and olefin. First we did was, let's look at the olefin. The top one was gas chromatography. This one is proportional counting. The first one here is 1 penting. During the course of steady state, we put 1 penting in. Here is we put 2 penting. The interesting point here is, doesn't matter you put 1 penting or 2 penting, we couldn't detect anything other than the material which is radioactive to start with. Okay. The rest of them, we thought the reaction is going to do a isomerization or hydrogenation or whatever, but we barely detect it. You can tell from here. Unfortunately, we would like to know the isomerization between 1 and 2 penting. What is that?
System trends.
System trends, I'm sorry. System trends, 2 penting. And unfortunately, this is equilibrium composition. If we can modify the composition, we probably can find out even this very fast equilibrium will be formed or not. I think that's an unfortunate point. The bottom line here is for 1 penting or 2 penting, or in general we say it is olefin, it's really hard to do anything. You just go in there and come out. Okay, that is a little bit surprise. For a long time, at least we think the olefin have a great chance to incorporate to a certain extent. But based upon that the incorporation is less than 3%. Okay. We say, okay, if C5 olefin is that lousy stuff, how about a higher hydrocarbon? So we did was we put one lysine during the course of the reaction. This time is a little bit surprised. You can tell that 14% of one lysine was going to dicane, and 19% goes to transient cis lysine. So it's very interesting. So now the question you will ask is, why C10 is different from C5? Okay. Number 2 question you will ask yourself, what is the impact of the design? Okay. Well, one thing I think George talked about this morning is oxidation of butane to form maleic anhydride. In this particular reaction, I think you guys did in DuPont was to make a resin reactor to make it. Okay. The key thing is because you don't want to fully oxidize the butane to CO2. So you fully utilize the way that you design the reactor, although the resin reactor costs a lot, a little bit more than conventional, but you did it. Okay. So that is based upon the reaction you understand, you try to develop and fit into your reaction. Okay, so the same question I would like to ask Steve is, when you present your case, you talk about rotational that reactor, then how about economics when you scale up? Okay, is that going to present limitation? And now come back to this question. Okay, what does that tell us? And if you really think about that is, because C10 has a longer, especially in this case, slurry reactor, have longer residence time. So it provided the opportunity to go undergoing some other kinds of reactions. If you connect that to the reality, now you realize why certain companies try to do Fischer Tropsch, and they would like to do with slurry reactor. Why? Because for the lower hydrocarbon, they want to produce olefin, right? Because olefin is very expensive to be a co-monomer for polymerization. If you produce paraffin, that's worth about 7 cents a pound. If you make olefin, 20-some cents a pound. So there's a major difference. However, for higher hydrocarbon, they want to do is they make lubricant. Therefore, you want to form paraffin. Therefore, you use slurry reactor, you give enough time, let it hang in there long enough to form paraffin. Therefore, you maximize your profit margin. Okay. So that's the inside story that for a long time I didn't realize why see the name. There's certain company wants to pursue certain reactor configuration. Slowly when I look at it, I say, well, there's always reasons behind that. The reason is economics. Okay, bottom line. Just further illustrate this, the comparison between alcohol and olefin. We talk about alcohol incorporating, we talk about olefin incorporation. You can tell either ethanol or pentanol. The incorporation is much higher than ethylene or pentene. The reason, apparently, we don't know good enough, but you can tell they behave differently. The oxygenated compound over there helps the absorption there for whatever reasons. One of the key issues people always talk about is how the reaction going on. You know, we have Anderson shows Fourier distribution, which says it's stepwise reaction. But you know, let's from the mathematical approach. Let's do that. Is really let's try to put CO2. Okay, if we put the CO as labeled compound, it doesn't matter. Everything goes up, so you don't get any information. However, this time we put the CO2 as labeled compound. First, this is CO2 radioactivity. This is CO radioactivity. So that means the water-gas shift reaction is not 100% in equilibrium. For otherwise, it doesn't matter how much CO you put in there. If they reach equilibrium, they should have pretty much same radioactivity. So it's not. So that's one thing. Number two is, if somehow CO get some radioactivity and start to do the chain initiation, and what you will see is the curve, radioactivity curve should behave like this. However, in reality, we find out is radioactivity according to carbon goes like this. What it really says is we believe the CO2 as the initiation. That's why pretty much everybody has the same activity like this, and CO as the chain goes. That means CO insertion into there. And every time you got one extra carbon, you got a little bit radioactivity. That's why the curve is the experimental data like this. So what that says is, we do prove from this point of view that most likely CO insertion into the chain. Okay, it's not CO2. And the CO2 most likely is going to be able to initiate the chain. Okay, so that's demonstrated in this fashion. I think it's rather interesting. Now we talk a little bit about reaction. Just 2 minutes. In this particular slide, what we did was with different catalysts. Okay, it's a carbon number, this is radioactivity. You can tell when the carbon number goes up, the radioactivity goes down a little bit. Theoretically, if we put, in this case, I think we put ethylene. Okay, we should expect that pretty much horizontal because we believe ethylene pretty much initiates the chain, but in reality, it's not. So this is a Fischer reaction. The reason is because you always have a little bit of accumulation in your catalyst, okay, which will dilute your radioactivity, especially with a higher hydrocarbon. You have this tendency. That's why it drops a little bit. Okay. However, if we go to a slurry reactor, now we compare with Fischer reactor versus slurry reactor, you'll find out is the radioactivity decrease is quite dramatic. The reason, again, because of secondary reaction, there's some other things going on, accumulation. So you don't truly detect whatever you're supposed to detect. And let's come to the original point, really, is whenever you got all those data, I always look this way, is how can I apply those important information to put into industrial application? And how can I utilize those information to design the best way for this particular kind of reaction going on and mix the best economics. So to the end, talk about summary. I know everybody, most of people here don't like to talk about economics, but really I think being in the industry for more than 10 years, I like to. And that's a little bit about this aspect. For the unsupported ion cat, because basically we talk about unpromoted ion cat. This is our summary. Apologize for the twist slide. Alcohol, 1 and 2 alcohol behave differently, which is quite clear. And alcohol incorporates much better than corresponding olefin. We don't know exactly the reason. accumulation in the slurry rack and complicated data interpretation, but in certain cases, it will be going to be good for your application because you identify where you want to go. Here, of course, we can you can tell that based on our work, you can use quantum forming to investigate the reaction mechanism. Last one is tricky point. Before I end up this, I would like to appreciate Dow Chemical giving me this opportunity to present here. There are some other co-workers back when I was in Kentucky. We did together with this. I'm glad to entertain everybody here.
Questions?
Well, you asked me a question about CEO's private life. Which we help each other taste the wine. Hey, after so many years, I still couldn't tell the difference between that and wine. Although you try very hard to teach me, CEO.
David, I got a question for you. About C14, why that isotope? Is it because of the type of counter you're using, and the lifetime of it?
We use a proportional counter. It's kind of things when the stuff goes through a furnace, you burn to CO2 and counter. This is in gas phase. In liquid phase, what we did was we go through liquid gas chromatography, high pressure liquid chromatography, collect a sample and go to a counter, Geiger counter to counter the radioactivity. Yeah.
Many years ago, when we were fooling around with carbon 14, we found that ethylene acted both as a chain initiator and also built in to the system, whereas the alcohol did not. Now, we didn't get around to doing any higher forms. You have. Do you find what differences you find in, say, just ethylene?
I knew Casey is going to ask me this question. That's the work you guys did about 1954. Personally, I cannot answer that question. It is a very interesting plot you guys made that back then was ethylene not only can serve us a chain initiator, but at the same time can be a propagator. If you really look, the case presented to us is a little difficult. For example, if we use, the reason is twofold. Number one, when you go to higher olefin, the incorporation is really, really small. You can tell from our presentation, you only incorporate about 3%. And if you go to the next C10, try to differentiate between 3% and probably 4% or 5% radioactive, it presents a hard time.
Maybe the higher olefin is just hydrogen to the paraffin.
That's correct. Yeah. Well, higher. Yeah. When you go to really higher, you have a tendency to just go to paraffin. So the competition between the chain initiated and hydrogenation become more severe. So to answer your question, so we couldn't get any solid data to prove yeah or nay. Okay, does that answer your question?
Sure.
George?
Just wanted to know, were there advantages to using carbon 14 with a radioactive detector as opposed to just carbon 13?
Very good question. I think this question has been asked several times when we go to different. I think one time I went to a USDOE meeting.
Do you answer it differently?
Well, it depends on person. Okay, good friend, I answer true. Truly. I think.
But in this case,
we'll find out momentarily. I think it's clear in Lehigh University. He did a lot of C13 stuff. If you really look at the C13 cases, it's very, very good technique. You can identify between C1 to C4. After C4, then the isomers is so much, you are going to have a very hard time to differentiate the difference to certain extent. That's to my understanding.
Because
There-
of cracking.
Well, because they have so many isomers. For example, C4, you only have how many isomers? No, 6, no, 8. Okay, if you go to C5, or in our case, when you go to C10, there's lots of isomers. Okay, in our case, what C6, C7, C8, we try to do is we try to identify every single one. That's the reason why we can tell the difference between 1C8 and IC8, or what transient 6, and so on and so forth. I think that would be a limitation for C13 case. That's to my understanding. Okay, because it gets so complicated. I don't think you use any technique you can successfully identify. Well,
But to the carbon-13 at 7 atmospheres, the amount you would have to use would be $100,000 or something to run for 4 hours.
And you think that's a limitation?
Well, it was when Lee Min was there, but now he's at Dow. He could afford
Yeah,
it.
now I can do it.
well, we are thinking about do C13 for something, but I cannot share with you. Yes, it is very expensive.
So you're saying the sensitivity of detection for C14 is so much higher?
Yes,
That's
Absolutely.
certainly true.
Okay.
Absolutely.
by factors of 10 to the 9th or something.
The other problem is,
And the cost is
Yes.
not higher by so many factors. How many factors?
Oh, it's
well, comparable.
Comparable?
A couple of times higher. If we made in houses, same thing, right? Even
no.
cheaper.
The carbon-13 per gram is very expensive compared to carbon-14. For $40, we can make at that time a mole of the reactant, but to make a mole of with carbon-13 would be $100,000.
I hope that's autofocus.
I hope it is. This close could be tough, yeah.
The other problem is natural abundance.
Thank
That
you.
is that you have 1% carbon-13 in
That's
everything.
right.
And you're going to have to use a mass spectrometer to differentiate it. When you get out to carbon-10, 14, anything large ones, and you're looking at the difference between the natural abundance, which is 14%, let's say in a carbon-14, and the amount you've added. It gets much smaller.
I think that's true. That's very true. Thank you.
nobody ever used carbon-13 to look at the inspection you have to have. It's all the trouble. Special laboratory.
Well, also, you have a carbon-14, you have a big, huge, humongous molecule. You have to really know the cracking pattern down to the nth degree to differentiate between what's 10% incorporation and what's 15% incorporation. Because it doesn't give you a single peak in the NMR, I mean, in the mass spec. It gives you a cracking pattern.
We're gonna meet back here at 1:30 for the next talk